All right. Good morning, everybody. My name is Mike Malakamati. I'm a member of the Data Management and Statistics Core for the Arizona ADRC. I'm very proud to present this talk and webinar in our continued educational series that we're putting on. Today's speaker is Dr. Anna Capuano from the Rush University ADRC. Dr. Capuano is an associate professor of neurological sciences and faculty statistician of the Rush Alzheimer's Disease Center. Dr. Capuano serves as the elected vice chair in the executive committee of the Design and Data Analytics Professional Interest Areas Assembly of ISTART. With over 80 original peer-reviewed publications, Dr. Capuano's work was cited more than 4,500 times. She has worked on several international, multiracial, multilanguage studies and collaborates with neurologists, neuroscientists, and other researchers in the application of modern statistical methods in epidemiological studies and clinical trials that seek to understand environmental and behavioral risk factor for age-related conditions. Dr. Capuano's methodological interests include longitudinal models, nonlinear mixed models, and constrained ordinal class models, as well as study design and disparity research. Right, and just a couple of housekeeping things before we start. Please be sure to keep your microphone on mute during the presentation. You can submit questions for Dr. Capuano through the chat function, and she will answer those at the end of the talk, and I will moderate those questions for her. So Dr. Capuano, the floor is yours. Please go ahead and start.
Thank you so much for the kind introduction, and thanks for having me. So today we are going to talk about the sigmoidal mixed effect model. So this paper is in statistical methods in medical research. You have the link if you want to grab the paper while we are discussing it. So just leave it here for a minute. Okay. So when to use this model? So this model is a nonlinear model that can be used for longitudinal data and especially on cognition. It requires that you have a Gaussian outcome, and you do want a monotonic nonlinear trajectory, meaning that you don't want the data to go up and down, right? The trajectory will be smoothly declining or smoothly increasing, depending on what you're studying, in our case, decreasing. And you need at least 5 observations per participant, although we are doing some research internally, and it looks like if you have a certain amount with 4, it's okay. But you're going to see the publications that I'm going to share with you, and the method we use at 5, so conservatively. You also want this, the time of these longitudinal observations to be anchored at a point. So we talk about DAF as the anchor point, but in other researchers, you can have the birth, for example, as an anchor point. And at that point, you have asymptotically like a level that the person reaches, right? So, we have also need a reasonable number of predictors. So it's not a model that you want to super saturate and have everything that you can imagine on it. It's already a complex model. So you want to be careful about it. Maybe look at one predictor at a time and then build your model. You can put multiple predictors on it. So this is an example, it's a spaghetti plot of what we have for global cognition, just to give you an idea. So, for example, these participants, this is time from death. When they come, we may have a stable cognition, maybe declining just a little bit, but as time progresses towards death, the decline slowly accelerates. And for some people, it drops a lot. These are some some specific plots. I just want to share this so you can see how the data looks like. So you can have, as the data collected, sometimes you have a point that is very low and things like that. But overall, the model fits very well to the data. And here I'm just for a brief comparison, is just you have the change point model that assumes two lines and one change point underneath it, so in light gray. So let's talk a little bit about the model itself now. Now, bear with me because we have some formulas here, but we are going to just talk about the interpretation of the parameters. And so it's important just to show the structure. So this is a nonlinear mixed effect model. So we are going to have fixed and random effects on obviously a error term. So this is the structure. So the first parameter that I'm going to talk about is this level at depth. So in a linear mixed effect model, for example, where you have two parameters, you have the intercept and the slope, right? So in the intercept, you can have there a couple of predictors, for level, and then for change, you can have other predictors. Here in this model, we are going to they have the ability to put predictors not only for level at depth, that's this one, but also for level earlier. So this is the parameter that represents the level at depth. And basically, as it increases, you have, higher level at depth. Okay. So the next parameter would be the limiting level before decline, so earlier. So that's a projection, so it's limiting. That's why it's limiting. This would be the other level where we can put predictors. So for example, for earlier level of cognition, maybe education will be significant, and then you can put education for that, but maybe for level at depth may not be, or for level at depth you want to examine something else that makes sense. Another example that I'm going to show you later is BMI. So we look at BMI earlier in the study, and then BMI at depth. So you can put those two levels in associated to different parameters as it makes sense. So for this, then you're going to have, if you have a higher parameter, you have higher level of cognition earlier. Okay. So next, let's see. So the next one is the half decline. So half decline represents the point in time, and this is the parameter. So it's at the time where half of the total decline that the person will experiment already occur. Okay. So for example, in this figure, you see that the top line, the person is coming very stable, and then close to death, then the person really starts to decline very fast. So the half decline will be closer to death, while this other person in black here, the person is already declining, earlier and steadily, but faster than the others. So the half decline will be earlier. And then the rate of decline, it's about like the shape around those parameters. And so basically, I'll have another slide that you will be able to see with more details, but it's that curvature around the change point. Because people may have same level at DAF, same around, same level earlier, and same change point, but then the curve is different. So the model is flexible to get that. So this is the illustration of that, right? So the person has same level as the other for at DAF, same earlier, same half decline, but still the curve is different, okay? So we can capture that. And so this data tree represents this parameter, can be used to calculate then the proportion of decline. So when time is equal to the time of half decline, this proportion is going to be half, right? And then it can be more or less, depending on where you are in the curve, you can calculate that. So I brought an example just for us to understand the output that we get and how to interpret these parameters more directly. So this is a small sample from Ross, and Ross, as many of you know, is a cohort of Catholic nuns and priests and brothers, and they are enrolled without dementia, and they have annual clinical evaluation. So we have, for example, global cognition calculated every year for them. And at DAF, they donate their brain, and then we obtain pathology, all that stuff, right? So this is so this is a sample of 149 women. The education is high, 17 years on average, and we have at least 5 observations for them. We can go up to 20, so 20 years of data. And at baseline, they are enrolled with, on average, with 77 years of age, and then they are around 8 on average. So, and then the global cognition is based on 19 tests that are Z-scored. And this is kind of the structure, just so you guys see the structure that we have in the data for analysis. We have an ID, and then, for example, education is collected at the baseline, so it's the same. Then you can Z-score it. Then you have time from DAF, is changing, right, as for each visit. And then you have this global cognition calculated every year. So to run the sigmoidal, you can do that in SAS. There is a macro that was developed for it, and it's available at GitHub. And then here is the link for you guys. The macro, you basically need a couple of informations for you. So needs the name of the data, and then you need a variable for time from DAF, or example of time for DAF, but it can be another time variable. Then the ID that tells that all this information belongs to the same person, right? Then the outcome variable, and the reference time, it would be, okay, for this data, the deep change happens around what, 3 years. It's just a reference, and this will help us with the seeds for the model. Then the macro provides a graph, and so you can feed 2 points for it to obtain the graph. So 2 values of the predictor. So it can be based on the quartile. For example, you can provide the first quartile and the last quartile, and we provide the curve for those 2 points, two values. And then the plot maximum time is because the plot will be plot on time from 0 to whatever maximum time you gave. So it's, you need to give something that is reasonable and within what you observed, right? So this is how you feed that data. So here, just for example, so time is time from death. The reference time is 3 years. So about 3 years, I'm thinking for terminal decline. So we just gave that value as a reference, and the score of education, and then we are going to plot, have the plot to up to 8 years, and because it's the predictor is the scored, I'm just saying the values will be -1 and 1, right? For us to look at the graph. And if you want to, you can also just go ahead and use mix to model the sigmoidal model, and the paper actually has sample codes for you. So if you go back to the original paper, you have example of codes that you can just modify for your data and do something more sophisticated if you want. So this is the output, how we are going to get the data out, the results out. So you have the 4 parameters. You have the effect of the predictors on those 4 parameters, and then the variance covariance structure. And so for this first parameter, it's going to be the level at death. And so let's observe here that we have the effect, the level is minus 0.9. The effect of this predictor, that's education, on the level is 0.04, okay? So now let's see how we would, let me move you guys here. Okay, so what does that mean in the curve, right? So here we have the 2 curves that we obtain with the -1 and +1. Remember that we have this score of education. So people with higher education, they come higher, and then they're towards the end declining faster, which is something that we observe, we have been, discussing the literature on threshold of pathology, right? So with higher education, you hold your cognition longer, but then possibly there is this threshold of pathology that then people start to decline faster. So this is just an example, not. And then this is higher cognition and this is lower. And here we are going to see the level, we obtain the level at that. So we got that estimate 0.9, and it's +1, right? Because we are assuming z of education equal 1. And then when we add those 2, we have -0.8. That's this value. Then the next one is, we do the same thing, but we are going to subtract because it's -1. So again, subtract 0.04, and we are going to have -0.9. That is this value, okay? So very straightforward. And so the next, here. So the next parameter that we are going to talk is the data form, jumping to, and that's the level before decline. So again, a level parameter. And now we look at we have estimate is 0.8, and the effect on the estimate of education is 0.19. So we are going to do basically the same thing. But remember, this is a projection, right? So we get 0.8, we add 0.19, and we have a 1. So we think that projecting, this is the level that the person had stable earlier. Then, and remember, we are plotting 8 years here, but we have more data than this. So the next one, we get 0.8, and we then subtract 0.19, and we have 0.6, and projecting, that's what we think the person had. So, and again, we can put multiple parameters on that as it makes sense. for the research question. So the next parameter is going to be the half decline. I particularly like this parameter. I think it's very interesting. It can help answer some research questions. So let's take a look at this in the plot. So again, theta 2 is estimated as 4. The predicted, the effect of the predictor on it is minus 0.7. So now, so here is the half decline, right? It's a point in time. So for people with higher education, so we're starting with 4, we're going to add the estimate, and this estimate is negative. It's going to be 3.3 years, okay? So it's closer to that, right? Same thing we're going to do for lower education, but now we are subtracting, and it's going to be 4.8 years. And so they are having the half decline earlier than people with higher education. So the next parameter is about the shape of the curve, right? So this is, we are going to call that rate of decline. And now you see that we have data tree that's 0.8, and then the effect of the predictor is minus 0.07. So how can we translate that? So we have the half decline that we calculated. So we are here in this example, I'm going to just talk about the higher education, but you know, you can do the same thing for lower education, okay? So we have the half decline, that's 3.3, and we can calculate then the theta 3 for these people with higher education, doing the same thing that we did before, just adding the effects, you know, by the predictor. So we have a 0.775. So with that, we can calculate the proportion of decline at each given time, at each point in time. So we have theta 2, that is the half decline, and we have the theta 3, that's the rate of decline. Now, with this formula, we can see how much decline they had per point. So for example, at the half decline, if you plug here 3.3, you're going to have half, so 0.5, right? And if you, and then depending on what point you plug here, you can have more or less. At def, you're going to have 1. So at def, you decline everything you decline, right? It's the end. So you can also fit this model in R. So I'm just showing some code here, and this is a work that I did with my dear postdoc, Maud Wagner. That is, this should be here also in the webinar, and so she's doing a tremendous job in making this available for R, and we are doing also other works with the Sigmoidal. So just to show you other examples of things that we look with this model. We look at pathology and how the shapes of this trajectory would be different by pathology. So this we did with ROS and MAP. So we have 420 older person, and MAP recruits from the community, in contrast of ROS that we just discussed, that they are religious participants. But we also, for the entire sample, we have annual visits, and here we also use at least five observations. And we are looking at the entire trajectory to death. So these people died, and then we have the pathology available. So in this example, in this article, what we could do, we could put this pathology in the model and see when people have a lot of, this is a representation of people have a lot of each pathology, what is the trajectory in comparison? So you can see that TDP is really, it makes you lose, start to decline much earlier, very nonlinear, very smooth, and but much faster. If you don't have pathology, that's the reference line here. This blue line, you hold pretty well cognition till you have those last years of before death. The next one is really bad is tangles, as you guys probably would guess. And this is another plot that you can, do with this curves. And so when we look at different levels of the pathology, if you don't have the pathology, is the situation where it comes very well, and you may, in this case, declines at the end. If you have a lot of the pathology, then it comes much earlier and smoothly, and you're going to end up in a worse situation before death. So another example is this, that we look at BMI and pathology. And here again, the link of the paper, if you guys want to grab it. And here, so here we use similar sample was later, so updated a little bit, but we included BMI. So we were in the original paper, we look at BMI very simplistically without pathology, but just to understand instability of BMI. So if your BMI is bouncing in the sense that you have a bad year and then come back, even if you recover that BMI and come back to a better BMI, that's already bad for you, basically. There are different ways to this is a parenthesis, but there are different ways that we look at BMI. Some people look at slope, or just one point, right? We have a lot of studies that just look at BMI at baseline, but having longitudinal data on BMI is informative, and especially because of this instability of BMI. So BMI usually decreases with in older age. In this age group, that's a concern, right? People get very fragile. But also that having a bad year when you get very sick and maybe lose a lot of BMI, or get very swallow and end up increasing your BMI a lot, even if you recover that stable range, we call, because we do some mathematics around in the corners of the BMI, but that value, if it's high, if this delta is high, it's very associated to bad cognitive outcomes. So this is this would be the trajectory with BMI. So a stable BMI gives you you have with a higher cognition, and this trajectory is better till eventually you also other things happen, and then you also decline. So we are to observe here that the midpoint for people with unstable BMI is earlier than for people with not stable, right? So it's not stable is earlier than for stable. So what we did in this example, in this paper, is then we put pathology, and we look if how much change we had in the estimates of the BMI. And you can see that when we put amyloid, BMI range is still significant, but the estimate is much smaller. So what happens is that when you plot it, instead of having that much difference in half decline, it's going to be very small. It's explained a lot by amyloid, which is very interesting if you start to think about, well, what's happening, right, to raise more research questions for us to investigate around BMI and pathology. The rate of decline is interesting too. It was significant as when you pathology becomes non-significant, it kind of explains how that curve is shaping, right? The type of curve. And note also here for the modeling perspective, where we can then put initial BMI, last BMI for level. Once we put this other information, then this is not as important. So this is interesting because there's so much discussion around BMI. As you guys know, high BMI is protective, there is bias, and that's why it's protective. So those types of models can give us more insights on those problems, looking at them at different angle, right? So I think that's what I had for you guys. I hope you found it interesting and helpful. We are going to have a workshop coming up in the next AIC in San Diego. I hope it's going to be in person, you know, and the workshop we're going to be the three of us, Don Hedker from University of Chicago, is a veteran on longitudinal models. He has a book that, as you may know, it's widely adopted for the topic. And so very happy that he accepts to do this workshop with us. And Dr. Graziella Muniz is a brilliant biostatistician, has a lot of work in change point models, and she will also be there in the workshop, and this is going to be a hands-on workshop. So I think it's going to be very, very interesting. And lastly, I would like to have my thanks and acknowledgements to Don Hedker and Jeffrey Dawson that worked with me on the development of the model, and the RIDC that in different ways, you know, we work as a team, so there are direct and indirect contributions to the work, especially Aaron Buckman that work on the BMI problem and pathology, Dr. Bob Wilson that work on the pathology, the initial paper, and my postdoc Dr. Maud Wagner. And with that, we can chat and okay, I see that Mike put the paper there. Thank you. If you guys have questions, I think we are ready for that, right?
Yes, and if we can go ahead and if you want to just put your questions into the chat box, I will moderate those to Dr. Capuano. And while we're waiting for the first questions to come in, thank you, Dr. Capuano, for the excellent talk. Really enjoyed it. Also want to let everyone know that the recording of this presentation will be posted to the YouTube page of the Arizona Data Management and Statistics Core. And I will send that link out to everybody who's registered for this webinar later today. All right, so we do have some questions coming in. The first one is, have you applied these methods to high frequency assessments or measurements? For example, hundreds to thousands of observations.
Not yet, but I think it's very doable, and it will be interesting to do so. So it's Justin Miller, right? So except what type of outcome do you have in mind, if you wanna share?
And our next question, oh, sorry, go ahead.
Yeah, and maybe we can go, but yeah, I think we haven't done that yet, but I think it's very reasonable to use this structure on this type of data.
Right, then our next question is from Dr. Abner. Does the requirement for 5 observations induce survival bias? What happens to the model performance when fewer minimum observations are used?
Okay, so we are, very good question. We are playing with that right now. We are working on a paper where we are going to give more recommendations on, what types of things you want for the model, and also comparing with other models, right? Because this is not exclusive from this model. Every time we look at nonlinear, and we will end up having this potential bias. So, and even if you go very low and assume just 2 observations and assume linearity, right? Still the bias can be there. So we think that we can use at least 4 observations. The modeling really can use long follow-ups though. And that's how we characterize the curve. So kind of you borrow a strength. If you have part of the sample that is, don't have a lot of follow-up, if you have a lot of people with a lot of follow-up, that's very helpful. We know this is a long process. It's, yeah, we imposed this earlier, the 5 points, because of the complexity of the model. And yeah, so that's a good question.
And the next one dovetails very nicely to that one. Is the minimum of 5 observations also dependent on scale or spread of these observations?
Yeah, so this is another thing that we are testing. So the spread is, so we are talking about annual visits. And if you think that, just thinking about that, with other models, we learned that terminal decline, like if you assume 2 linear slopes, right, linear slopes and a change, with those models, we learned that maybe that flip happens around 3 years. So you don't really want to have, very little, a lot of spacing, it's not ideal, but we tested when you have some spacing and more like distance of follow-ups, not annual, but more distance. And but a lot of data, right? Still with a rich data set. And it seems that the model is robust to having more spacing. But there are a lot of other things that can happen. When you're collecting data, there's missingness of that stuff. So that's the work we are doing now, looking at all those things. But so far, we've been having, good signal that it can space a little more and still be okay. But especially if you think that people are going to decline later, if you miss 2 observations, then you may miss the opportunity to observe where the data is curving, but you see that point down and that point up, right? The more granular, the richer the data you have, the best, that's for sure.
Dr. Marsiski asking if there are code examples in the manuscript, and do we have this available in R instead in addition to SAS?
Yeah. So yes. So the paper has examples in SAS, like open code, like with NLMix and stuff on. So I'm just going to show you. Sorry, go to it. Let's see. Sorry, it's there first. Let me just put. So at GitHub, you can just go there and grab the macro you see, and then you can play in SAS. I'm going to make available the R code for Sigmoidal there too. Yeah, you can model in R. It's possible. So that's something new. I realized that we are having less and less SAS users, right? I think Mike can agree with me. They were always migrating fully to R, and not fully, but this kind of split maybe. And
Nobody
so
wants to pay $8,000 a year.
What is that, Mike?
Nobody wants to pay $8,000 a year for SAS.
I know. And yeah, there are pros and cons, and I think that's a whole nother webinar.
Yeah.
But I think it's good to have a company that really will have, people that are, doing that as, but have some quality assurance, all that stuff, so things don't disappear and stuff like that. But R is amazing because there are so many scholars developing things for R that you can, have new things, and it's free, which is you can get better than free, right? So I figured that it was important. So we are with Dr. Wagner, we are working on getting that available.
Our next question comes from Dr. Chen. So when discussing the education effect, the linear model is assumed for each of the parameters, such as theta 2. Is there any likelihood that the theta would be a nonlinear function of age and maybe other variables?
That's a very good question. The model can accommodate that. I haven't played with that, so I would invite you to, maybe give an example and just run with an example and share with me. It'll be interesting. We haven't really played with nonlinear within, but it's possible that the association is not linear. Yeah.
And have you used other anchor points in your models, such as baseline, age at baseline? So
yeah, that's a good question. No, not baseline. I think you want something like my perception is that we may play with this, and maybe there are specific settings, but I think you need a strong anchor that means something biologically, I think, because remember, this is although you can have different curves. Oh, it's too bad that I didn't bring a graph for you guys. The model is very flexible in terms of curves. You even can have almost linear. And what's going to happen is your half decline is going to be thrown to very high value. If that happens, the model is telling you that, oh, this is actually linear. Okay, so there is, okay, I lost the question now. Is that again? I took a side.
It's okay. So there was asking if you could use study baseline.
Yes, sorry. So, I mean, you want to have. So although you can have linear, you want to have that asymptotic value of starting, and then it declines to another value, right? This is kind of the structure. So we haven't played with baseline because I don't think it makes sense. To be honest, for cognition specifically, right? You can be playing with another outcome. usually linear is pretty okay for earlier, when we are looking at from baseline. Now there may be other settings, or, even if you're looking at an outcome that is a lab value that has this clear timing thing, then you can anchor in other points. But in our setting, for combination, it makes sense to anchor a DAF. Yeah.
And then our next question is, this is a very good one. I like this one. How do we account for practice effects in these models?
You have to go to the workshop coming up. So, well, there are other methods, other models that are better to examine that research question, and we have detected a little bit of learning effect with other models, but we don't think it's big enough to cause a big problem. We keep incorporating. In other settings, though, if you have a learning effect that's too big, then you have maybe to exclude. You have to think about a way to incorporate that data that is not exactly the same thing, right? But there are some abrupt models, for example, the change point, right? You can examine learning effects with those. We did that in the past. So yeah, so there are so many tools that we can use, right, at these, and that's what we are going to explore in the workshop. So,
and we have another question from Dr. Chen. So the model fitting procedure is a numerical optimization process. How will the initial values and the number of iterations affect the model fitting?
So that's a good question. So we usually we want to use informative initials. So I know that you've been doing that, because that's a very practical question. The macro you'll see if we open it, you see that we use the data to grab informative initials, and that will help tremendously to fit the model. Regardless where you start, you should be getting something very similar. Otherwise, there's something goofy going on, right? But then, as you said, it will take a while for the model to convert and to find a solution. So I would recommend to use, informative initials, at least for the key parameters, and then so you see when you look at the macro, you understand. But you can, for example, look at level. You can have an idea of level using data, and that's how we are doing with the macro. We are grabbing this information and then make it easier for the model to run. You can also start, if you start, say, let me go to the next one. If you go with NLMix, for example, you can start with zeros, and see what value you get. But our experience is that you want to work with informative initials.
And while we're waiting for any other questions that come in, I actually have a question. So, in my thinking, and in a lot of the work that I do, we tend to think in terms of clinical trials, and in particular, what's the best way to model, change from baseline or treatment effects in a clinical trial. So, so right now the standard, approach is to use a mixed model repeated measures, which is, gives you a least squares estimate of, change from baseline differences in placebo and treatment. So, I guess my question would be, do you think that, this sigmoidal mixed model could be applied and actually be more sensitive to treatment effects, thereby reducing the sample size that would be required for a prevention study?
I think the issue is the timing. We go back to that time anchor, right? So when you're doing intervention, you are working on the middle of the trajectory. So this person is alive. He comes to your clinic, you give an intervention. You're going to follow for a couple of years, and then you're going to see if it's better or not, right? Usually, unfortunately, in clinical trials, we cannot follow for many, many years. It's a limitation, right? It's because of feasibility. It's just not possible, right? Maybe. And that's a real challenge that we have, because this is a very long disease, right? It happens very slowly over time. So my perception is that this model probably is not the best to look at this type of problem, just because of the timing, right? You don't have enough time to see. You may have some nonlinearity going on, but you don't have enough time to see something asymptotic going on, and the anchor would not be adequate regardless, right? Because you have an intervention, yes, no, and you're following from that point. So would be a little analogous to the question of following from a baseline of a research, right? Sort of. However, if you suspect there are no linearity going on, there are alternatives that you can employ to examine that, right? So, but I would not recommend the sigmoidal, though. The sigmoidal is a tool for other types of research questions. That's, although I would like to say that's good, but the reality is that as biostatisticians, we have a toolkit, right? Models are not perfect. They are just, we're trying. I like the sigmoidal specifically because it has you can interpret parameters, right? Mm-hmm. When you go to, splines, and you start to go into a sphere that you can't interpret, you can look at graphs. But even though those models also have a room, in research, it's just another tool. So we grab the tool that makes sense with the data, and that's why it's important for us to keep updated on the new models and things that are available. So at given a situation, you can think about, okay, this is the design, this is the data that I'm having, what type of tool I can use here. Is that the same? And like you said, it's good to explore other possibilities for analysis. And so we need to keep doing that. I think it's important.
All right. There are any other questions that we have for Dr. Capuano? You can put them into the chat. I haven't seen any come in the last minute or so. And again, just to remind everybody that the recording of this talk will be on a YouTube page that I have for the Arizona Data Management and Statistics course. So if you're unable to attend for all of it, or somebody else wants to see it, the link will be up very soon for it. So if there are no other questions, we'll go ahead and conclude. Dr. Capuano, thank you very much for your time and lending your expertise to us for this webinar series. I do appreciate it very much.
Hey, thanks for having me. I think that's a wonderful space for, to share and learn. So thank you so much for having me here.
Quite welcome. I hope you'll have a good rest of the day and a good weekend. And you'll probably see another email coming up in the spring for our April webinar that we will likely have. So please stay tuned for that. Thank you all.